Hello everyone, this is Mustofa. I am from Ingram School of Engineering from Texas State University. Here in this research, we are focusing on co-optimizing spacecraft routing and depot location allocation in deep space. So what we are doing in this research, we are actually minimizing the total mission cost so that it's easier to go from Earth to lunar to moon surface. Here, if you see the previous launch cost in Vanguard in 1957, there is a humongous cost. It's 894,000 per kg. So if you just save 1 kg of total mission mass, it will actually we can reduce equivalent of 1400. If you see in Falcon Heavy 2018, 1400 USD per kg. So what's the novelty of this research? We are considering the dynamic depot location allocation model. In this cislunar logistics network, we are launching from low Earth orbit, and our demand points, we have 12 lunar base demand points. So here we have 6 candidate depot and 12 lunar base, and the model assumption we are considering there is a uniformly distributed random material demands. The whole model lies on our classic rocket equation formulated by Konstantin Tsiolkovsky, and we actually derive this equation to find our fuel mass, structure mass, and our required payload. And here the total mission mass, we are launching our mission from LEO, that is low Earth orbit. So that is, we are minimizing depot mass segments or also base mass segment. And here the binary variables are which depot is open, which depot is serving in which lunar base, and what type of configuration. Either a single stage rocket we are using or 2-stage rocket we are using. So we can see in any sci-fi movies that after a certain time there is a portion of the rocket is discarded from its entire so that it can reduce their mass and it can go beyond. So that is called 2-stage rocket or 3-stage rocket. So we don't know which one is the optimal one to reduce the total mission mass. So we are considering single stage and 2-stage, and what we have found that out of 6 candidate depots, 5 are sufficient to meet the demands of 12 lunar base. And here, for both in every occasion, 2-stage rocket outperforms single-stage rocket, and for 140 combination, we need to consider the 12 optimal points. So we have these 12 optimal points, and if you see the equation, we have our ISP, that is specific impulse, what kind of fuel we are using. So we are using currently 450, that is hydrogen, liquid oxygen. But if you change the fuel type, if you change to ISP 600, that is electrical arc, we can save 23%. So what we got from these results, that 2-stage rocket actually saves almost 5,000 kg, that is equivalent to 10 million USD. And the future direction, we can incorporate ISRU, that is in situ resource utilization. Instead of establishing depot, we can have a factory over there and we can meet the demand. And also we can expand this network to Mars as well. Thank you so much.